Hello, this is the first video I'm making for the extra pre-cal material. So you'll be expected to take notes on this. I might even pause the video and try to answer the questions or do the examples before I actually do them. That way you're actually thinking about what's going on. And I will talk to you and probably check these notes later on. So, sequences and summation notation. So, the first thing we're going to talk about is what exactly is a sequence. Well, it's basically just a set of numbers that go in some kind of order. So, for example, there's such a thing called the Fibonacci sequence. One, 2, 3, 5, 8, 13, 21, 34, 55, 89, so on and so forth. You get the numbers in the Fibonacci sequence by taking the previous two numbers, which if I write in the magic pen, which will be in yellow, that's not something you necessarily have to write down. But this is gotten by taking the first two numbers and adding them together to get the second number. There it goes. So 1 plus 1 gives us 2, and then 1 plus 2 gives us 3, 2 plus 3 gives us 5, so on and so forth. Now, this is almost like a function. It's almost like a function where the domain, like a function. Where the domain would be the positive integers, 1, 2, 3, 4, 5. And the range, or the output, would be the terms 1, 1, 2, 3, 5, etc. So almost like f of 1 is 1, f of 2 is 1, etc. Except for we use a different notation. We use a lowercase letter with a subscript. So for instance, A1 is 1, A2 is 1, A3 is 2, etc. And if I want to talk about the whole sequence, I use a set of curly braces like that. Now, I'm going to read you this definition. You don't necessarily have to write it down, but I do want to read it to you. An infinite sequence, a sub n, is a function whose domain is the positive integers. The function values, or terms, are represented by a1, a2, a3, so on and so forth. Sequences whose domains consist of only the first n positive integers are finite sequences. So those are terms that have not an infinite number of, or those are sequences that have not an infinite number of terms. They're denoted as finite sequences. All right. So, write the first four terms. So here's a sequence defined as a sub n equals 3n plus 4. So if I'm going to write the first four terms, first I'd have to figure out what a1 is. Well, as you might guess, a1 is 7. 3 times 1 plus 4. a2 would be 10. 3 times 2 plus 4. a3 would be 13. And a4 would be 16. Now, suppose that this sequence, whoa, not b to the nth power b sub n, geez, is equal to negative 1 to the nth divided by 3 to the nth minus 1. So for b1, you would plug in 1 for n. So this would be negative 1 half, because 3 to the first minus 1 is 2. b2, negative 1 squared would be positive 1, and 3 squared minus 1 is 8, so that's 1/8. b3, negative 1 cubed is negative 1. 3 cubed minus 1 is 26. Oh, I'm out of room. We'll do b4 over here. b4, negative 1 to the fourth is 1. 3 to the fourth minus 1 is 80. Now, the way this works, if you had a continuous function, okay, like take this for example, it's pretty easy to tell this is that this one right here, I forgot you can't see me waving my arms. This one right here, it's pretty easy to tell that this is going up by 3 each time. Well, you could draw a line with a slope of 3, like so, you know. But if you're plotting a sequence, it's not going to be a continuous function because it doesn't have a domain of all real numbers. It has a domain of the integers. So instead of a graph that looks like that, it would have a graph that looks more like this, where you've got what's called a discrete set of points spread out that represent each one of the terms in the sequence. Now, the next thing I want to discuss is what are called recursion formulas or recursive formulas. So terms are defined using previous terms. In general, this is a pretty simple way to represent a sequence. It's not very easy to work with, but it's fairly easy to represent it. So for instance, if I had A1 equals 1, A2 equals 1, and AN equals AN minus 1 plus AN minus 2, for n greater than or equal to 3, that's a recursive definition. So starting at 3, this would be like A3 equals A2 plus A1, A4 equals A3 plus A2, etc. That's what this means right there. So, that's a recursive way to define the Fibonacci sequence. So here's another thing. Write the first 4 terms of the sequence A sub n if A1 equals 5 and AN equals 3AN minus 1 plus 2 for n greater than or equal to 2. Well, the first term's easy. A1 is 5. So then, I'm going to use this piece right here. I'm going to say, okay, A2 would be 3 times A1 plus 2. So 3 times 5 plus 2 would be 17. So A2 would equal 17. So 3 times 5 plus 2. A3 would be 53. Because that would be 3 times 17 plus 2 using this recursive formula right here. And then A4 would be 161. Because that'd be 3 times 53 plus 2. For some reason, I was going to do 3 times 52. And I got myself all fouled up. All right. So that's basically how a recursive formula works. Now, the next thing we need to discuss is what's called a factorial. So if n is a positive integer, positive, not 0. Then n factorial, now please note this is not n, it's read n factorial. It's basically the product of all the numbers from n down to 1, all the integers from n down to 1. So this would be n times n minus 1 times n minus 2 dot 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 times 2 times 1. So like 5 factorial is 5 times 4 times 3 times 2 times 1. And we define 0 factorial to be equal to 1. That doesn't make a whole ton of sense because, I mean, 0 is not a positive integer, and why would 0 times whatever be 1? But what that does is that makes a lot of math with the factorials work out very, very nicely. So with that having been said, let's write the first 4 terms again. A sub n equals 2 to the nth over n minus 1 factorial. And by the way, that's not a recursive formula. That's what's called an explicit formula because you can plug n directly into it. You don't have to use the previous terms. Like if I want to find A100, I could just plug 100 in. I don't have to know what A99 and A98 and A97 are and so on and so forth. So let's churn this out before the video ends, and then we'll finish this up later. So A1 would be 2 to the first over 0 factorial, which is 2. A2 would be 2 squared over 1 factorial, which is 4 divided by 1, so that's 4. A3 would be 2 cubed over 2 factorial. 2 factorial is 2 times 1, which is 2. 2 cubed is 8, so that's 8 over 2, which would be 4. And then A4 would be 2 to the 4th over 3 factorial. 3 factorial is 3 times 2 times 1. So this would be 16 over 6, which is 8/3. I guess I have a minute to bring up something else. If I have to do 10 factorial over 2 factorial times 8 factorial, I could write that out. This could be 10 times 9 times 8 times 7 times 6, and then I could write out all the stuff underneath it, like so. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all over 2 times 1 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And the key is, notice that this 8 and crap back here cancels with this 8 and stuff back here, and you end up with 45. And I'm out of time.